This video covers Part 2 of Section 1.2, Logical Equivalence. We're going to start by looking at the negation of a conditional statement. From the definition, the conditional P implies Q is false exactly when its hypothesis P is true, but its conclusion Q is false. That is, exactly when P and not Q is true. It then follows that the negation of P implies Q is logically equivalent to P and not Q, as shown. This equivalence can also be verified by constructing the truth tables of these compound statement forms. We can use this equivalence to simplify negations of compound statements involving the conditional. This result can also be generalized when negating the statement form P implies Q, where P and Q represent compound statement forms, to obtain not the quantity P implies Q is logically equivalent to P and not Q. Note that we cannot negate a conditional by distributing the negation over the conditional. Not P implies Q is not logically equivalent to not P implies not Q. For instance, when P and Q are both true, not P implies Q will be not true implies true, which is not true, which is equal to false. But not P implies not Q will be not true implies not true, which is false implies false, which is true. So these two statements have different truth values, so they cannot be logically equivalent. For our first example, we want to find a simplified form of the negation of each of the following statements. First we have, if 7 is an odd integer and 6 is an even integer, then 42 is an odd integer. As shown in a previous example, using the statement variables, P is 7 is an odd integer, Q is 6 is an even integer, and R is 42 is an odd integer. This has symbolic form P and Q implies R. The negation of this statement form is then not the entire quantity P and Q implies R, which is logically equivalent to P and Q and not R. So to obtain the negation of this conditional, we keep the hypothesis alone, change the conditional to an and we negate the conclusion. Translating back into English, this reads, 7 is an odd integer and 6 is an even integer, but 42 is not an odd integer. Next, consider the statement, if 7 is an odd integer, then 6 is an even integer only if 42 is an odd integer. Using the same statement variables as in Part A, this statement has symbolic form P implies the quantity Q implies R. The negation is then not the entire quantity P implies the quantity Q implies R, and this is logically equivalent to P and not Q implies R. So to negate the conditional, we keep the hypothesis P alone, change the conditional to an and we negate the conclusion, which in this case is Q implies R. And this simplifies further to P and Q and not R. So we need to apply the equivalence for the negation of a conditional twice in simplifying the negation, once when negating the entire statement form, and again when negating just the conclusion, Q implies R. In English, the negation of the original statement is then 7 is an odd integer and 6 is an even integer, but 42 is not an odd integer. You'll notice that this is exactly the same as in Part A. So both the two statements in Parts A and B both have the same negation, which means that the original statements must have been logically equivalent to begin with. Next up, we have if 42 is an odd integer, then neither 7 is an odd integer, nor is 6 an even integer. Once again, using the same statement variables as in Part A, this statement has symbolic form R implies not P and not Q. The negation is then, we negate the entire conditional, and this is logically equivalent to R and the negation of the conclusion, not P and not Q. And this is equivalent to R and We're negating an AND statement, so we have to negate each part of the AND, change the AND to an OR. So we have R and not P or not Q. And this simplifies further to R and P or Q. In order to simplify the negation of the conclusion, not P and not Q, we apply one of De Morgan's laws. We also use the double negation equivalence to simplify not P and not Q. Next, we need to translate the symbolic form of the negation, which is R and the quantity P or Q, back to English. This will be 42 is an odd integer, and either 7 is an odd integer or 6 is an even integer. For the English form of this negation, we need to be careful to indicate the grouping of the two parts of the OR statement, which we can do by separating it from the conjunction with either. For instance, if we were to just write 42 is an odd integer and 7 is an odd integer, or 6 is an even integer, we obtain an ambiguous statement which could correspond to either of the statement forms R and the quantity P or Q, or the quantity R and P or Q, which are not equivalent to one another. Next, we want to look at the converse, contrapositive, and inverse of a conditional statement. The conditional is one of the most important statement forms in mathematics because so many mathematical results are stated in the form of a conditional. Associated with a conditional statement, P implies Q, are three additional conditional statements. The converse is Q implies P. The contrapositive is not Q implies not P. The inverse is not P implies not Q. The converse is then obtained by interchanging the hypothesis and conclusion, the contrapositive by interchanging hypothesis and conclusion and negating each, and the inverse by just negating the hypothesis and conclusion. Be careful not to confuse either the contrapositive or inverse with the negation of the conditional, which we've shown is not quantity P implies Q is equivalent to P and not Q. In both the contrapositive and inverse, the hypothesis and conclusion of the conditional are negated separately. The converse and contrapositive in particular play important roles in mathematical proof, so we often need to be able to determine the converse, contrapositive, as well as the inverse of given conditional statements. It's also very important to understand the equivalences associated with a conditional, which we examine in the next example. So in this example, we want to find pairs of logically equivalent statement forms among the conditional, P implies Q, the converse, Q implies P, the contrapositive, not Q implies not P, and the inverse, not P implies not Q. The most straightforward way to determine which, if any, pairs of these statement forms are logically equivalent is to just construct a combined truth table containing all of them. So we'll have a truth table as shown, and we'll fill in the columns one at a time. From their truth tables, we see that the original conditional statement is logically equivalent to its contrapositive, and the converse is logically equivalent to the inverse. So P implies Q is logically equivalent to not Q implies not P, and Q implies P is logically equivalent to not P implies not Q. And we recognize that these are really the same equivalents with just the roles of P and Q switched. However, there are no other equivalences among these statements. In particular, the original conditional statement is not logically equivalent to its converse. So P implies Q is not logically equivalent to Q implies P. Assuming that a conditional statement is equivalent to its converse is one of the most common mistakes students make when trying to prove mathematical results. For our next example, we want to find the converse, contrapositive, and inverse of the following conditional statements. First we have if 7 is an odd integer and 6 is an even integer, then 42 is an odd integer. And As usual, we translate this to symbolic form using the statement variables. P is 7 is an odd integer, Q is 6 is an even integer, and R is 42 is an odd integer. The statement has symbolic form P and Q implies R. The converse then has symbolic form R implies P and Q. For the converse, we just switch the roles of hypothesis and conclusion, which reads in English as, if 42 is an odd integer, then 7 is an odd integer, and 6 is an even integer. The contrapositive has symbolic form not R implies not the quantity P and Q. For the contrapositive, we interchange hypothesis and conclusion and negate each. And now this is logically equivalent to not R implies not P or not Q, where we've used one of De Morgan's laws to simplify the negation of P and Q. This reads in English, if 42 is not an odd integer, then 7 is not an odd integer, or 6 is not an even integer. And finally, the inverse has symbolic form not P and Q implies not R. For the inverse, we simply negate the hypothesis and conclusion. This is logically equivalent to not P or not Q implies not R, which reads in English as, if 7 is not an odd integer, or 6 is not an even integer, then 42 is not an odd integer. For our next example, let's look at the statement, if 7 is an odd integer, then 6 is an even integer only if 42 is an odd integer. Using the statement variables from Part A, this has symbolic form P implies the quantity, Q implies R. The converse then has symbolic form Q implies R, quantity implies P. We switch the hypothesis and conclusion to obtain the converse. And this reads in English, if 6 is an even integer, only if 42 is an odd integer, then 7 is an odd integer. The contrapositive has symbolic form not the quantity Q implies R implies not P. And this is logically equivalent to Q and not R implies not P, where we've used the equivalence for negating the conditional Q implies R. This reads in English, if 6 is an even integer, but 42 is not an odd integer, then 7 is not an odd integer. And finally, the inverse has symbolic form, not P implies not Q implies R. And this is logically equivalent to not P implies Q and not R. And this reads in English, if 7 is not an odd integer, then 6 is an even integer, but 42 is not an odd integer. We saw earlier that a conditional statement is logically equivalent to its contrapositive, but not to its converse. For instance, the calculus theorem, if the function f is differentiable at a point x equal a, then f is continuous at a, is logically equivalent to its contrapositive, which would read, if the function f is not continuous at x equal a, then f is not differentiable at x equal a. It is not, however, equivalent to its converse, which reads, if the function f is continuous at x equal a, then f is differentiable at a. In fact, the converse statement is not true in general. It's easy to find examples of functions which are continuous at a certain point x equal a, but not differentiable at that point. For instance, the absolute value function, which is defined by f of x is the absolute value of x, is negative x if x is less than 0, and x if x is greater than or equal to 0, is continuous at x equals 0, but is not differentiable there, since its graph has a corner at x equals 0. For another example, again from calculus, one of the theorems on infinite series states, if the infinite series a sub n from n equal 1 to infinity converges, then the limit as n tends to infinity of a sub n is equal to 0. This is logically equivalent to its contrapositive, which reads, if the limit of a sub n as n tends to infinity is not equal to 0, then the infinite series of a sub n does not converge. The theorem in this form is often called the nth term test and can be used to show that a series diverges. Given an infinite series, if the limit of its nth term does not equal 0, then we can conclude that the series diverges. The theorem is not, however, equivalent to its converse, which would read, if the limit of a sub n is equal to 0, then the infinite series a sub n converges. Again, the converse is not true in general. The standard example of an infinite series whose nth term has limit 0, but which does not converge, is the harmonic series, the sum from n equal 1 to infinity of 1 over n. I want to next consider the biconditional. The biconditional, P if and only if Q, means P if and only if Q, which can be rewritten as P if Q and P only if Q. Since P if Q has symbolic form Q implies P, and P only if Q has symbolic form P implies Q, it follows that the biconditional statement satisfies the equivalence P if and only if Q is logically equivalent to P implies Q and Q implies P. This equivalence can also be verified using a truth table. Many mathematical theorems have the form of a biconditional statement. To prove such a theorem, we need to show that the statement is true. This equivalence shows that proving a biconditional statement, P if and only if Q, is true is equivalent to showing the two conditional statements are true. The statement P implies Q and its converse Q implies P. For our next example, we want to find a simplified form for the negation of a biconditional, P if and only if Q. We can first rewrite the biconditional as the conjunction of two conditionals, and then apply De Morgan's law together with the equivalence for the negation of a conditional. So we have the negation of P if and only if Q is logically equivalent to the negation of the quantity P implies Q and Q implies P. So now this is the negation of an and statement. So using De Morgan's law, we obtain this is equivalent to not P implies Q or not Q implies P. And now we have the negation of two conditionals, and so this simplifies further to P and not Q or Q and not P. And this gives us a formula for the negation of the biconditional. For an application of the formula, let's find the negation of the following statement. 6 is an even integer if and only if 42 is not an odd integer. Translate this to symbolic form using the statement variables. Q is 6 is an even integer, and R is 42 is an odd integer. The statement then has symbolic form Q if and only if not R. And the negation is then the negation of the entire expression, Q if and only if not R. And this is logically equivalent to Q and not R, or not R and not Q, which simplifies a little bit further to Q and R, or not R and not Q. In English, this reads either 6 is an even integer and 42 is an odd integer, or 6 is not an even integer and 42 is not an odd integer. Now we need to use the either in there to group the two parts of the or together. We're going to end this video with some cautions. There are a few things to take note of concerning how terminology is used in logic or mathematics and ordinary speech. First, in logic, a hypothesis and a conclusion are not required to have a causal connection. In ordinary speech, people would never say things like, if gas prices are high, then Star Wars was the greatest movie of all time. Or, if Pluto is a planet, then Abraham Lincoln was the 16th President of the United States. We generally formulate a statement of the form, if P then Q, only when there is some causal connection between P and Q. In logic, however, the two parts of a conditional statement need not have any causal connection. Therefore, both of the above statements are perfectly acceptable, and their truth values can be can be determined using the definitions and rules of logic. Second, in ordinary speech and sometimes even in mathematical texts, a biconditional is written as a conditional. The formal statement P if and only if Q is seldom used in ordinary conversation except for emphasis. Frequently, when people intend the biconditional, they will leave off either the and only if or the if and part of the biconditional and say only P if Q or P only if Q. For instance, a mother might tell her child, if you eat your dinner, then you will get dessert. Or you will get dessert only if you eat your dinner. In both cases, the meaning is you will get your dessert if and only if you eat your dinner. So the intention is a biconditional. This type of language occurs frequently in mathematics texts in the statement of definitions. For instance, a text might state, a positive integer n is prime if its only positive divisors are 1 and n itself. When the meaning is in fact the biconditional, a positive integer n is prime if and only if its only positive divisors are 1 and n itself.